Today, Danny and I will introduce about the continuity and the one-side limits. We will first find the continuity at a point and on an open interval. For a function to be continuous, it has to be unbroken. This means that there are no holes, jumps, or gaps. In other words, you must be able to draw the graph of the function without picking up your pencil. And here are 3 examples of functions that are not continuous. The first graph that fc is not defined is because there is a hole in the graph, and so this is not continuous. The second graph that the limit of x to c fx does not exist is because it is jump continuity, so it's not continuous. It's just jump. And the third function that is not continuous because the limit of x to c fx does not equal to fc. The definition of continuity. Continuity at a point. A function is continuous at c if the following 3 conditions are met with 1. fc is defined or exists. 2. The limit of x to c fx exists. 3. The limit of f to c fx equals to fc. Continuity on an open interval. A function is continuous on an open interval ab if it is continuous at each point in the interval. A function that is continuous on an entire real line from negative infinity to positive infinity is everywhere continuous. Now let's start with examples. Example 1. fx equals to 1 over x. This function is continuous everywhere except x equals to 0. The second function that fx equals to x plus 1, x smaller equal to 0, and x squared plus 1, x bigger than 0. This function is everywhere continuous. For the third function, fx equals to x squared minus 1 divide x minus 1. This is continuous everywhere except x equal to 1. If a function is not continuous, then we call it discontinuous. Discontinuities come in 2 types, removable and non-removable. Removable discontinuous could be made continuous by appropriately defining fc so that the function is continuous. And so there are examples of non-removable and removable. For the one-side limits, a limit can be evaluated from just a single side of point C. These are called the right-hand and left-hand limits. The right-hand limit evaluates the limit as the function approaches the point C from values greater than C, which is represented as limit to x to c plus fx. The left-hand limit evaluates the limit as the function approaches the point C from values less than C, which is represented as limit of x to c minus fx. Note, one-side limits can occur when normal limits do not. And see the example of evaluate the following values. The limit of x to 3 minus fx equals to 1. Like the black point shown in the graph. B. The limit of x to c plus fx. That is 4. C. The limit of x to 3 fx does not exist because the left side does not equal to the right side. And number D. f3 it is equal to 1. Example, evaluate the following limits. A. The limit of x to 2 minus 3x over x plus 4. Just have to take 2 into the formula, and then we got the value that is 1. For question B, the limit of x to 3 plus x minus 3 over x squared minus 9. This time we have to remove x3 from the denominator both upper and lower sides, and so we can get the formula, that is 1 over x plus 3. And so then we take 3 into the formula, and so the value is 1 over 6. For question C, the limit of x to 0 plus x minus 1 over x squared, the value is negative 1 over 0, which does not exist. The existence of a limit. Let f be a function and let c and l be real numbers. The limit of fx as x approaches c is L if, and only if, limit of x to c minus fx equals to L equals limit to f x to c plus fx. The left and right hand limits equal to each other. We can use this idea to extend the definition of continuity on an open interval to a definition of continuity on a closed interval. A function is continuous on a closed interval a, b if 1. It is continuous on an open interval a, b. 2. The limit of x to a plus fx equals to fa. 3. The limit of x to b minus fx equals to fb, like the graph shows. The function is continuous from the right and continuous from the left at b. The function is continuous from the right at a and continuous from the left at the b. And now let's turn our homework part to Daniel. So now I will discuss the homework part. Use a graph to determine the limits and discuss the continuity of the function. First, limit x to c plus fx. We can see here c is equal to 4, so fx is equal to 3. So limit x to c minus and x to c is all the same. And it is removable continuous. Limit x to c plus fx. Here we can see that the circle is at 0, so we can determine that the answer is 0, and it's removable discontinuous. The last one, limit x to c plus. We can see it from the right side, so the answer here is negative 3. And the limit x to c minus, we should see it from the left side, so the answer is 3. And the limit x to c fx, the left answer and the right answer are not the same, so it is D and E. And it's non-removable discontinuous. Find the limit if it exists. If it does not exist, explain why. Limit x to 8 plus 1 over x plus 8. We can put 8 into the denominator, and the answer is 1 over 16. Limit x to 5 plus x minus 5 over x squared minus 25. In the denominator, we can divide it into x minus 5 times x plus 5, and then the numerator and the denominator can be deleted, so it's only the 1 over x plus 5, and we put the 5 into the denominator. The answer is 1 over 10. Limit x to negative 3 minus x over the square root of x squared minus 9. We can see the x is negative, and in the denominator the answer is always positive, so the answer first is negative or then we can see the x become smaller and smaller, and in the denominator the answer will become bigger and bigger, so the last answer will become smaller and smaller, so it's negative infinite. Limit x to 0 minus x over x. We can see here so in the numerator it is always positive, and in the denominator it's negative, and the positive and the numerator and the denominator are the same, so it's negative 1. Limit x to pi over 2 secant x. It is equal to 1 over cosine pi over 2, and it's 1 over 0, so it's DNE. Then discuss the continuity of each function. Fx is equal to 1 over x squared minus 4. We can draw the graph, and then we can find that the x is not equal to negative 2 and 2. So this graph is continuous at all the points except x is equal to negative 2 and 2, where graph has asymptotes. Fx is equal to x squared minus 1 over x plus 1. We can see here x is not equal to negative 1, so this graph is continuous at all points except x is equal to negative 1, whereas there's a hole in the graph. Determine whether the statement is true or false. If it is false, explain why or give an example that shows it is false. If limit x to c fx is equal to L and fc is equal to L, then f is continuous at c. It is true because the left side and the right side are all the same, and it is equal to the limit x to c fx, so they are all the same. They are all equal to L. Every day you dissolve 28 ounces of chrome in a swimming pool. The graph shows the amount of chrome Ft in the pool after t days. Estimate and interpret limit x to 4 minus Ft and limit x to 4 plus Ft. First, let's say limits t to 4 minus. We can see it from the graph. It's equal to 28, and limits t to 4 plus Ft. It's from the graph we can see it's a black hole at the right side, so it's 56. Limit t to 4 minus Ft is the amount of undissolved chrome remaining in the pool at the end of the day 3, and right before more is added. Limit t to 4 plus Ft is the amount of the undissolved chrome right after more was added to the pool. So that's all the homework. Thank you.